Alright, so recently we've introduced some basic rotational kinematics formulas. Now we're going to look at some specific example problems and how to solve those problems using our new friends, those rotational kinematic formulas. So here's our first example. A merry-go-round rotates such that it completes 10 full revolutions in a time of 13 seconds. Please forgive the fact that seconds is spelled wrong. For whatever reason, Android tablets don't do autocorrect. I said, calculate the average rotational velocity of the merry-go-round in radians per second. Well, if you remember, we have angular velocity or rotational velocity is equal to the change in theta over the change in time. Well, first things first, we have to look at, well, what is our change in the angle, theta, in radians? Well, we know delta theta, we said it went 10 revolutions, and we know there's 2 pi radians in every one revolution. So revolutions, bing bing, we have delta theta would be equal to 20 pi radians. Very simple there. So we have our change in theta, 20 pi radians, over our time, which is 13 seconds, and 20 pi radians divided by 13 seconds gives us 4.83 radians RAD/seconds. So it's important to note that rotational velocity is indeed measured in radians per second. Alright, now we have a second example that is a continuation of the first one. I said, now the merry-go-round slows down for 25 seconds and its rotational speed is 1.2 radians per second at the end of that 25-second interval. I ask you to find the average rotational acceleration during that 25 seconds. So hopefully you remember rotational acceleration or angular acceleration is shown by this symbol, alpha. That's the first Greek letter of the alphabet, and that alpha is equal to the change in the rotational velocity over the change in time, just like our regular translational kinematic equations where acceleration is change in velocity over time. So on this, we know our final velocity is 1.2 radians per second, so we have 1.2 minus the initial from the previous problem, which was 4.83 over our time interval, which was 25 seconds, and some basic arithmetic here, and we get negative 0.15 radians per second squared. So once again, a very simple problem dealing with rotational acceleration. Alright, now for our last example, example 3, and forgive me if I rush here, my battery is about to die on the tablet. So example 3, I said a certain point on a rotating wheel is rotating with an angular velocity given by the equation. And this is actually an omega, not a W, but sadly the program here does not have an omega, so we're stuck with W, the thing that looks closest to an omega, that says the velocity is equal to 3t plus 5t squared. I said if the point has an angular position of 3 radians at time equals 0 seconds, calculate its angular position and angular acceleration at 2 seconds. So something we need to remember, that if I have a, let's go with position here, and it's a function, and I want to find the velocity, all I do is take the derivative of that function. And then if I have velocity and I want acceleration, I take the derivative of that velocity function. Well, going the other way, if I have acceleration, I would then take the integral of that function to get my velocity, and then going up the ladder here as well, if I have velocity, I would take the integral with respect to time for that to get the position. So let's go ahead and do our basic calc here and calculate those values. So looking through here, I have my original equation for velocity. That's omega t is equal to 3t plus 5t squared. Well, let's start and solve the angular position. So that angular position as a function of time would be equal to, we need to take the integral of our velocity function, so that'd be integral of angular velocity with respect to time, so that would be the integral of 3t plus 5t squared dt. That gives me theta is equal to 3 halves t squared plus 5/3 t cubed plus c. Well, if you remember, I told you it had a position of 3 radians at time 0 seconds. So guess what? C, that constant, then becomes 3. That was the position at time 0. So all I need to do now is plug in 2 for the time, and due to space restraints I'm not going to show all that work, but you do that and you get 22.3 radians, and that is our position at 2 seconds. Boom. The next one, I ask what's the angular acceleration. So I look here, I want angular acceleration alpha, and to do that I need to take the derivative of my velocity function, so that'd be d omega dt, and that's going to be equal to 3 plus 10t. So just like we did before, we're going to plug in 2 seconds there, and last time I checked, 3 plus 20 gave me 23 radians per second squared. So there you go. 3 basic rotational kinematics examples, and a little bit of calc tie-in, just some basic things that we should remember from before, but we're tying in rotation instead of translational motion.